What if the secrets to Yellowstone's explosive past lie hidden in ancient geological patterns? We're diving deep into the park's thermal anomalies, uncovering how forces millions of years old are still shaping its landscape today. Prepare to see Yellowstone not as a static marvel, but as a living, breathing testament to Earth's immense power. Picture Yellowstone National Park. Steaming geysers shooting skyward, bubbling hot springs in vibrant hues, and the faint rumble of the earth beneath your feet. It's not just a park, it's a geological time capsule, a place where the planet's ancient history pulses through every gush of steam and tremor. Yellowstone's thermal features, like Old Faithful's iconic eruptions or the prismatic pools of Mammoth Hot Springs, aren't just pretty sights. They're windows into processes that started millions of years ago, driven by forces so deep and powerful they've shaped continents. These hot springs, geysers, and fumaroles are the surface expressions of a massive volcanic system sitting atop one of Earth's most dynamic hotspots. Beneath Yellowstone lies a supervolcano, its magma chamber fueling the park's thermal activity. But this isn't just about what's happening now. It's about patterns that stretch back eons, telling a story of a restless Earth. By studying these patterns, we can piece together not just Yellowstone's past, but also its future, offering clues to when and how this sleeping giant might stir again. Why does this matter? Because Yellowstone's thermal activity isn't random. It's a rhythm. A heartbeat driven by geological forces that have been at play since the park's volcanic system first formed. Understanding these ancient patterns could help us predict future geothermal events, whether it's a geyser, next eruption, or something far more catastrophic. Let's dive into the story of Yellowstone's fiery heart and uncover what it's been trying to tell us for millions of years. Yellowstone's thermal features are powered by a hotspot, a plume of molten rock rising from deep within the Earth's mantle. This hotspot has been active for at least 17 million years, leaving a trail of volcanic destruction across the American West as the North American tectonic plate drifted over it. Imagine a blowtorch held steady while a sheet of metal moves slowly across its flame. That's how the Yellowstone hotspot has carved its path, creating a chain of ancient calderas from Oregon to Wyoming. Today, the hotspot sits beneath Yellowstone, feeding its supervolcano. The park's most recent major eruption, about 640,000 years ago, formed the massive Yellowstone caldera, a 30 by 45-mile depression that's still geologically active. The heat from this hotspot drives groundwater to superheated temperatures, creating the geysers and hot springs we see today. But these features are just the result of current activity. They reshaped by millions of years of geological evolution. Fossilized evidence like ancient hydrothermal deposits found in the park shows that thermal activity has waxed and waned over time. During periods of intense volcanic activity, geysers and hot springs were likely more widespread. In quieter times, they retreated, only to surge again when magma moved closer to the surface. These cycles, recorded in the rock layers and mineral deposits, reveal a pattern of activity tied to the ebb and flow of the hotspot's energy. To understand Yellowstone's thermal anomaly, scientists study its geological record like detectives piecing together a mystery. Rock formations, ash layers, and mineral deposits act as clues, showing when and how the hotspot influenced the landscape. For example, isotopic dating of zircon crystals in volcanic rocks has helped pinpoint the timing of past eruptions, revealing a rough cycle of major eruptions every 600,000 to 800,000 years. The last one was 640,000 years ago, which has some wondering if we redo for another, though geologists caution that these cycles aren't a strict timetable. Beyond eruptions, the thermal features themselves tell a story. Geysers like Old Faithful operate on predictable schedules, but their timing has shifted slightly over decades, influenced by subtle changes in underground plumbing systems. These shifts are driven by the movement of magma and fluids deep below, which can alter pressure and heat flow. By mapping these changes, scientists have found that Yellowstone's thermal activity fluctuates in response to deeper geological processes, like the slow inflation and deflation of the caldera as magma chambers fill and empty. Seismic studies add another layer to the puzzle. Yellowstone is one of the most seismically active regions in the U.S., with thousands of small earthquakes each year. These tremors, often too faint to feel, reveal the movement of fluids and magma beneath the surface. By analyzing seismic waves, researchers have mapped the hotspot's plume, which extends hundreds of miles into the Earth's mantle. This plume isn't static. It pulses and shifts, influencing the intensity of surface thermal activity over centuries or even millennia. Yellowstone's thermal features aren't just relics of the past. They're dynamic, responding to changes in the Earth's crust. Take the Norris Geyser Basin, one of the park's hottest and most active areas. Its geysers and hot springs can change dramatically in a matter of years, with new vents opening and old ones going dormant. In 2003, for instance, a surge in thermal activity at Norris caused ground temperatures to spike, killing trees and forcing trail closures. This wasn't a one-off event. It was part of a long-term pattern of thermal surges tied to magma movement. These changes aren't random. They're part of Yellowstone's geological rhythm. By studying sediment cores and tree rings, scientists have found evidence of similar surges stretching back thousands of years. For example, periods of increased hydrothermal activity often coincide with slight uplifts in the caldera as magma pushes the ground upward. These uplifts, measured by GPS and satellite data, show that Yellowstone's surface rises and falls by inches every few years, a subtle but constant reminder of the forces at work below. This living landscape also affects the park's ecosystem. Hydrothermal areas create unique microclimates, supporting heat-loving microbes that thrive in scalding waters. These extremophiles, some of the oldest life forms on Earth, offer clues to how life might have survived in Earth's early hostile environments. Their presence also ties back to the geological story. Mineral-rich waters, heated by the hotspot, provide the chemicals these microbes need to survive. So, what do these ancient patterns mean for Yellowstone's future? The short answer: nothing is certain, but the clues are compelling. The park's supervolcano isn't likely to erupt anytime soon. Geologists estimate a 1 in 730,000 chance of a major eruption in any given year. But smaller events like hydrothermal explosions or shifts in geyser activity are far more common and harder to predict. In 1985, a small explosion at Porkchop Geyser sent rocks flying hundreds of feet. A reminder that Yellowstone's thermal system can be volatile even without a full-blown eruption. Long-term trends suggest that the hotspot will continue to drive thermal activity for millions of years. As the North American plate moves southwest, the hotspot will eventually shift out from under Yellowstone, potentially creating a new volcanic region elsewhere. For now, though, the park remains a hotbed of geological activity. Scientists monitor it closely, using tools like seismometers, GPS, and gas sensors to track changes in real time. These efforts have revealed that Yellowstone's magma chamber is only partially molten, with about 10 to 15% liquid magma. Enough to fuel thermal features, but not enough to trigger an imminent eruption. Still, the ancient patterns offer a warning. Yellowstone is not a static system. Shifts in magma flow, earthquakes, or even climate change could alter the park's thermal behavior. For example, changes in precipitation could affect groundwater levels, which in turn influence geyser activity. A drier climate might reduce eruptions, while wetter periods could intensify them. Understanding these connections requires blending historical data with modern monitoring, a task that's as much art as science. Yellowstone's thermal anomaly is more than a geological curiosity. It is a testament to the Earth's raw power and complexity. Its hot springs and geysers are the surface echoes of processes that began millions of years ago, driven by a hotspot that's still very much alive. By studying the park's ancient patterns, we gain not just a glimpse into its past, but a roadmap for its future. Will Yellowstone erupt again? Maybe not in our lifetimes, but the forces shaping it are far from dormant. This is a landscape that demands respect and curiosity. It's a place where the Earth's history is written in steam and stone, where every eruption or tremor is a reminder of our planet's restless nature. As we continue to study Yellowstone, we're not just unraveling its secrets, we're learning how to listen to the Earth itself, tuning into a story that has been unfolding for millions of years and will continue long after we're gone.